what is your understanding on bonding?
It's when two elements
Hmm.
combine or
Okay,
like either give or share electrons to
very good.
form a new compound altogether.
Okay, so they lose or
Gain electrons.
gain, or they also share
Yeah.
to produce new product. Okay. Now, why do they have to lose and gain electron?
Uh, because doesn't the losing or gaining of electrons prompt energy losses and energy gains, which would then lead to a new product being made? I have no idea what I'm saying.
Okay, I'll give you a hint. Octet. Does it ring a bell?
So the shell requirement is fulfilled.
Okay.
Like
What
there
is
has to be electrons, right? Like four pairs of electrons in the outer shell for the element to be satisfied and unreactive.
uh,
So that's why elements
or
lose.
or elements would get depressed?
Yes,
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 sir. You,
yes.
you cannot use the terms not satisfied. Uh, Rather, it has to do with the stability.
Stability. Oh, I knew there was an S word, just forgot the S.
Okay.
Which
So
one it was?
so you just came up with satisfied.
Yeah.
Okay. See, the idea is when an atom has octet again, which no, which means 8 numbers in the valence shell,
Mm,
leads to stability of the atom.
yeah.
And how do we know that? What is the proof we have? How do we know having 8 in the valence shell leads to stability?
Um, well, wouldn't that be like, isn't that what like most elements like strive to do in a way? Like, and that's why the
Yeah,
last group of
but
elements.
yeah, but who told them no? It's if you get 8 electrons in the valence shell, you will become very stable. How do we know that? What is the evidence we have?
Uh,
Okay, noble gases.
yeah, so the last group of elements because they're
Yeah,
like unreactive and they have full shells.
very good. No, no, don't say full shells because
Oh,
they have octet, not full shell.
okay,
I'll tell you why. Okay, first, noble gas is helium. That's an
mm,
exception. It doesn't have octet. It has only 2 electrons, and that is completely filled.
yeah,
Then neon, which is 10. Now it becomes 2 and 8.
8, yeah,
Organ, which is 18, it becomes 2, 8,
2,
and 8.
yeah,
But what is the maximum for third shell?
8, no?
No. How many electrons third shell can occupy?
Oh my days, is it the whole 2p?
Don't worry. Let's not get into that. Just remember this formula, 2n squared. Okay.
Okay,
So n represents the shell number. If I put
okay,
one square, it becomes 2. So
okay,
first shell can accommodate only 2. Second
mm,
shell can accommodate only 8. So what
okay,
would be for third shell?
18,
18. right? So here the fully occupied state would be 8,
Oh,
right? That is why no, it wouldn't make sense if you use the phrase no fully occupied
yeah,
shell,
full shell. Okay.
right? That would be
But it
wrong.
does that happen? Like shells with 18 electrons?
It happens. For example, the next element, helium, neon, argon, krypton would be 36. So it would be 2, 8, 18, 8.
Whoa.
Do you understand? But
Okay.
again, you can see krypton, the fourth shell, again, maximum would be
Eight.
4 versus 16, 32. But we don't have 32 electrons. We just have 8 electrons.
Eight. Okay.
So do you understand? So all the noble gases has octet in their valence shell. Not,
Okay.
so we you shouldn't write fully or completely filled valence shell,
Yeah.
right? So that
Okay.
would mean different.
Yeah.
So now knowing that all the halogens have octet in their valence shell, and also knowing its property of being highly stable and least
Yeah.
reactive, it doesn't react at all, very very stable in nature, right? Which
Yeah.
why all the other elements also want to attain such stability, and
Yeah.
to do that they take different routes. So it depends on the element. So metals usually have a very less number of electrons in their valence shell, which makes them lose their electron easily to attain the octet. You get
Okay.
that?
Yeah.
Again, there are few exceptions. For example, let me, yeah, lithium 3. So 2 and 1. I'm not
Yeah.
writing, we can also write 1 as 2, 2 as 1. Um, so this we can understand with a very simple configuration, 2 and 1. Now, lithium again is like, it cannot get octet because it already has only 3 electrons.
Yeah.
The best uh, s- stability it can attain is that of heliums having
Yeah.
two electrons. So lithium loses that 1 electron, which makes it lithium plus. You understand? So
Yeah.
similarly, sodium would become sodium plus, potassium becomes potassium plus. So all the group 1 elements will have,
Lose.
I think you might have learned, I'm not sure, about the group properties.
Reactivity. Oh,
Yeah.
okay, never mind. Yeah, yeah, yeah.
So group 1 elements,
Reactivity increases as
very
you go
good,
down.
very good. And why?
Um, doesn't it have something to do with the atomic radius getting bigger? So that's why the electronegativity between the nuclei and the last electron getting like
Okay.
lesser. So then the first ionization energy is like much less than the first element in the group.
Wait. And don't pull in all
No?
the concepts.
Okay.
You're
No?
pulling in
Okay.
all the concepts. Don't complicate it. Uh,
Okay.
okay. So this is very closely associated. So I'll explain that also. So tell me, what is reactivity? What is your understanding on reactivity? When we say potassium is more reactive than sodium, what do we mean by that?
If you drop potassium in water, it'll
Yeah,
fizzle out
we know,
fast.
right? Like it burns.
Yeah.
Sodium
Yeah.
doesn't burn, it fizzles,
Yeah.
giving hydrogen smoke. But
Yeah.
what exactly is happening inside? What
Well,
makes potassium more reactive?
potassium just loses that one electron quicker than sodium, no?
Very good. So when we talk about reactivity of metals, so even you have reactivity series, right, of metals. what are we comparing? Just the ease at which, the metals lose their electrons. We know metals are capable, or metals like losing electrons, but how quickly, easily they lose it makes them, it is comparative based on how easy and how quickly, with how little energy they absorb and release the electron. We talk about the reactivity as very reactive, less reactive. You understand? And
Mm.
when I say potassium is more reactive than sodium, again, very easy to understand. Why? Because sodium, 1, 2, 3 shells,
Yeah.
valence electron in third shell. Potassium, 4 shells. So fourth shell
Yeah.
is like
So then its atomic radius is more.
yes, ionization potential and all connected.
Ah,
But to explain this, you don't need. Okay.
okay.
So the idea is, since the size is bigger, the valence
Yeah.
electron is away. And
Yeah.
also the number of inner electrons, means inner electron shielding, is higher.
Yeah.
Yeah, shielding effect is there, and the size is there, the distance is there. So makes potassium remove the electron much easier.
Mm,
That's
yeah.
so. Okay, very good. So now, if you look into the number of valence electrons in group 1 elements, they all will have one. Lithium
Yeah.
2, 1, sodium 2, 8, 1, 2, 8, 8, 1. It goes on like that. So all the group 1 elements will lose one electron, making them
Oh, these
mono.
elements each up to 18. Like, couldn't it be 2, 8? No, that doesn't work.
Here,
Never.
this is an exception,
Oh,
right? I hope. Have you learned these electronic configuration with orbitals?
the PSD.
Yeah.
Yes.
What? You're not very clear there?
I'm not very confident with it. Not really.
Okay, I'll give you. Potassium is 19.
Yeah.
Can you give the electronic configuration?
Okay. So first I have P where there's two. So that's gonna be wait, I need to draw this
Yeah.
out.
Yeah, write it down and tell me the answer. It's also fine.
1, 2. Okay, and this is 2P, 2. And then what's after P? S, right? Is it?
It starts with S.
Oh my God, why did I start with P? Anyways, 2S2. Okay. And then right after 2S2 is P.
Mm-hmm.
That's gonna be 1, 2, 3, 4, 5, 6. Okay. P6, right? Yeah, P6. And then D is 10. Okay, yeah, anyways. So that's in 2, mm, 6, 11, um, 2S2, 2P6. There's no, so that's gonna be 3S2, 3S2, 1, 2, and then 3S6, maybe?
3s6.
No, 3P6. I meant 3P6. I
Oh,
meant 3P6.
okay.
Okay. One's 9, and then 1, 2, 3, 4, 5, 6. So then that's 3. And then you go into D.
Just
mm,
19 electrons. Don't keep on writing. Count the electrons also.
3. Um, I don't know if this is right.
Yeah. No worry. Just tell. We'll see.
Is it 2S2, 2P6,
Two
3S2, 3?
straight away to
Oh, there's one as well, isn't there? I thought about it and then I went,
Mm,
is there one?
of
I'm
course.
so yeah, okay. But that doesn't change much, right? So it goes 1s2, then 2s2, right? Right?
Mm-hmm,
Yeah. Okay.
mm-hmm.
That's four. And then we have 2p6
Very
and
good.
then 10. And then we have 3s2, which will be 12. And
Very
then
good.
we have 3p6, which will be 18.
Mm-hmm.
And then we'll have um 4s 4s1,
Mm.
which was 19. And that's gonna be 19.
Okay, why did you go to 4s after 3p?
Because doesn't 4s fill up faster than 3d? Because you need more energy to fill up 3d than you do with 4s,
Okay.
right?
4s has lower energy than 3d.
Yeah, 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 yeah,
Yeah, so which means it 4s gets filled first. Then,
yeah,
so now,
3d.
yeah, so now you can see 1s represents the first issue.
Yeah,
So this is what we have written as 2 here. This
yeah,
then 2s 2p together 8.
yeah.
3s 3p together 8 and
One,
4s we have written as
one.
okay. So
Yeah.
I think you know it, but you need some practice, I guess.
Yeah, that's it. Like I know the concept, but I'm not very confident with it. That's all.
Okay, you
Yeah.
have to work out, no, you have to practice.
Yeah.
You just randomly write for all the maybe from 1 to 30 elements, right? Atomic.
Mhm.
But you just
Yeah.
try, it'll be helpful. If not,
Yeah.
if you have doubt, also you let me know, we'll work out. Okay. Okay, now the point is the metals, for example, group 1 metals having one valence electron, it is easy for them to lose that one and becomes monopositive ions. Same way,
Mhm.
group 2 metals will lose two
2 plus.
electrons
Yeah.
becoming dipositive 2 plus ions. So this is the way in which metals attain octet easily by losing their electrons. Parallelly, non-metals on the other hand, for example, O8, 2 and 6, right? So non-metals, instead of losing, it is easy for them to gain
Yeah.
electrons.
Oh, never mind. Yeah.
Yeah, so again, why not lose electrons? See, again, the uh, currency is energy, right? In atom, the currency is energy, and it is energetically costly.
Mhm.
Removing 6 electrons would be costlier. So it is easier for the atom to gain 2 electrons, which makes them O2 minus.
Okay.
Nitrogen 7, 2 and 5. So it takes 3 electrons, becomes N3 minus. You understand?
Yeah.
Okay.
Yeah.
So
Yeah.
now I'll tell you one more thing. O2 minus, N3 minus, F minus, neon, sodium plus, magnesium 2 plus. All these we can call it as isoelectronic species. Okay.
What?
Isoelectronic, it might be a question, okay, in your
Okay.
MCQ. Isoelectronic is nothing but has same electron numbers.
Ah, like in total,
Yes,
like
so
after they lose and gain.
oxygen 8, again 2 minus, so plus 2, 10.
Yeah.
So
Yeah.
all will have 10 electrons.
Ah, okay.
So these species are called as isoelectronic species. They might give you any combination. This is just an example, okay? They might give
Yeah.
you from anywhere in the periodic table. This is a simple
Yeah.
example. Yeah. Okay. Now, for metals and non-metals, we understand, especially uh, like when the number of electrons are lesser, they lose it. When the number of electrons are higher, and it needs few more electrons, it gains,
Yeah.
and by that way they attain octet. But what
Yeah.
about element like carbon? Yeah, and see, it is like again a business. Only when there is a buyer, there will be a sale, right? Without a buyer, there won't be any sale. So similarly, a metal will only lose its electron readily when there is a non-metal which can gain it.
Mm-hmm.
So that is why when a metal comes together with a non-metal, a chemical reaction happens, forming
Mm.
an ionic compound. I'll talk about
Yeah.
this. I think ionic compound we would have learned again, right? The basics. But
Yeah.
the point is, metal loses the electron easily. And see, one more thing that you have to understand is metal already does not have neutral atoms. For example, when I take sodium, they are not sodium atoms, they are already as sodium ions because the electrons are delocalized. This is what you learn as metallic bonding.
Ah, yeah, with the sea of electrons.
Yes, very good. C of
Yeah.
electron. But the electrons are still inside. It is not,
Yeah, yeah, yeah. Yeah.
it has
Not
not
outside.
been
Yeah.
released, right? Still
But they're more free moving.
yes, they are just present in the same space within the metal. But
Yeah.
when a chemical reaction happens, the electrons are actually lost to the non-metal.
Mhm. Yeah.
But when it comes to non-metals like carbon, right?
Yeah.
2, 4, 2 and 4, right?
Yeah.
Now you can see it is in the very middle of the octet.
Isn't carbon like doesn't carbon rarely form ionic compounds though? Like isn't it much more likely to be in covalent bonding?
Yes, very good. So the reason is it is equally no costly, like both gaining electron and losing electron. One thing, carbon is a non-metal, which means it is more capable of gaining electron. Secondly, even if it has to gain electron, it has to gain 4 electron. Even it has to lose electron, it has to lose 4 electrons. So
Mhm.
which is why some metals choose sharing of electron
Yeah.
to attain the octet again,
Hmm.
right?
Yeah.
And this happens when we have two non-metals coming together. When two non-metals come together, we no, we can witness them sharing electrons.
Yeah.
Okay. So why do we call the bond between a metal and non-metal as ionic bond?
Cause
Hmm, come on, you can answer to the name ionic bonding.
oh, because it creates an ion, like a negatively or positively charged atom.
Very good. So metal becomes positive ion, non-metal becomes negative. So sodium with Cl2, for example, chlorine gas, we get sodium chloride,
Yeah.
right?
Yeah.
So sodium will become sodium plus, and chlorine atoms becomes, so I'll write it like this. Sodium loses electron, becomes sodium plus, and chlorine molecule
Gain
uh,
electron.
gains. So chlorine molecule has two atoms, so 2 Cl minus, it has to gain 2 electrons. Do you understand
Yeah.
this? So in order to balance this, 2 electrons, only 1 electron here, I just take 2 sodium atoms, 2 sodium ion, 2 electron.
Isn't this the half equations? No,
Uh,
the ionic equations
kind
when
of
you just
oxidate. Yeah, kind of. This is redox half
redox
reaction.
reactions.
Yeah, very simple. See, wait, I'll write it again. Wait, I'll write it again. Okay.
No, it just gave me like flashbacks, like traumatic flashbacks from IGCSEs.
Yeah, I just want you to understand. Okay. Very
I
simple.
struggled so much with this last year.
Don't be scared. Okay. We know that sodium loses electron, right?
Yeah, yeah,
So that is what I'm writing it as. I
yeah,
also know that sodium loses only 1 electron.
yeah.
So sodium ion plus an electron. Chlorine molecule, I know it gains electron,
Yes.
but in
Mm,
one chlorine, since chlorine is a diatomic molecule in nature,
yeah,
there's 2 atoms. You get that? So I need 2 electrons, 1 per atom, to get
yeah.
2 Cl minus.
2Cl minus, yeah. No, I remember how to do it. It's
Okay,
just I got like sudden like
I
flashbacks.
get it.
And
Okay.
my
If you know, it's
goodness.
fine. Don't worry.
Yeah.
Okay, so 2, right?
Yeah.
Okay, now how do we define ionic bonding? So this sodium is a positive ion, and positive ions are also called as cation,
Cations.
right?
Because catapult.
Because,
um, because cats have paws and it's a positive ion.
okay, that's a way to remember. No, what I did is I ask students to remember like this.
Oh, that's good as well. That's
Yeah,
really good
just
as
the
well.
T you
Yeah.
can remember as positive.
Yeah. Our chemistry teacher last year told like went with the whole paw way and just the whole chem exam I just heard someone whispering, was it cation? Because cats have paws.
Okay,
Yeah.
he knows, he knows. That's a good
Yeah.
one. Anions, N you can remember as the negative. So
Negative. Yeah.
if you remember one, the other one is opposite.
Yeah.
So sodium is an ion, positive ion, and chloride ion is a
Negative.
negative ion. So what is ionic bonding? Ionic bonding is the electrostatic force of attraction. Electrostatic attraction between, you can write it as cations and anions or positive and negative ions. Done?
Yeah.
Okay, so how do we define ionic bonding?
An electrostatic attraction between cations and anions.
What is electrostatic attraction?
Um, yeah.
Okay, just asking
The
questions
attraction
and everything.
between electrons.
Electrostatic, electrostatic, static is, again, it is a term we use in science, static charge, static.
Uh,
What's the opposite of static?
Um,
Dynamic.
Okay, I would have never guessed that.
Okay.
I would have never guessed that.
Static, dynamic. Static is when something is stationary. Dynamic, we know it changes, it moves, there is a motion,
Okay,
right?
okay,
So
okay.
static charge, maybe in lower classes, the very basics, rubbing the balloon with the, uh,
Yeah,
yeah. So all those are static charges. Charges are created, but they are just there. Once they are created, they are not moving anywhere. If
yeah,
charge starts moving, it becomes electricity. So the electricity is basically a dynamic charge,
yeah,
right? Static
yeah.
is something that doesn't move, that is stationary. So here, electrostatic means electric charge, which is stationary, right? This is for your understanding. You don't have to write this,
Okay,
no, in detail in your exam. Just to understand it very logically, very clearly, I'm giving you all this. Okay.
yeah,
So electrostatic attraction, which means electric charge, which is positive, negative charge, they actually attract. We know that the charge attraction is very real, and there is a real force
yeah.
of attraction between charges. So
Mm,
even inside the uh, ionic compounds, where it has a lot of ions, there is an actual force of attraction existing. And this attraction, electrostatic attraction, is what we refer as ionic bonding. And
okay,
when we talk about ionic compound, there is a one big difference between ionic compounds and covalent compounds, which is a covalent compound, you can have it as a single entity. What do I mean by that? For example, when I take water molecule, two hydrogen with one oxygen covalently bonded, we get
yeah,
water molecule, and there are lone pair of electrons. So this is one single molecule.
yeah.
But in ionic compound, we do not have that. We have millions and millions of ions regularly arranged in lattice arrangement.
Ah, but isn't that ionic crystals and not isn't
Yes.
isn't lattice more for covalent and
No,
then
no,
I
no.
crystals more for ionic?
Lattice arrangement is, what is lattice arrangement? How do we define lattice arrangement?
I
No,
don't know how to find it. I can like
you're,
show it.
you're doing some magic.
It's like when it's like repeating structures, right? Like,
Yes.
yeah.
Repeating three-dimensional arrangement, regular three-dimensional
Oh,
arrangement.
never mind. Okay, okay,
Right?
yeah.
That is called as lattice array. So it is like, you have, let's say you have 1,000 plastic balls or not
Yeah,
tennis balls, and you have your floor, right? Your bedroom floor, and you are just starting in one corner,
yeah,
and you are just arranging very close to each other.
yeah,
So you will be having a three-dimensional arrangement, right? You'll
yeah,
finish one layer first, then on the first layer, you'll be stacking the second layer.
yeah,
So this layer wise, proper arrangement is called as three-dimensional regular arrangement is called as lattice arrangement.
lattice. Yeah.
And here, there is no other option because a positive always attracts a negative, right?
Mm,
And a
yeah.
negative always attracts a positive.
Positive.
No
Yeah.
other go. And
Yeah.
in higher classes, you also learn about uh, imperfections in the lattice arrangement. It is not as perfect, not 100% perfect. There will be some lattice imperfection, but overall, don't keep all that in mind. But just for now, think that it is completely arranged plus minus throughout.
Mm,
So here we don't have, when I say NaCl, we don't have one NaCl anywhere. An NaCl, it is made of millions of Na plus Cl minus regularly arranged. And why do we say ionic compounds are crystalline in nature? Because how crystals are formed when particles are regularly arranged, it results
Yeah,
in crystals,
yeah.
right?
But is it necessary for you to have a positive and negative, like an electrostatic attraction for you to form a lattice arrangement?
That is what uh, no drives the arrangement. See, if the particles ought to arrange themselves, so we know that according to particle theory, when you decrease the temperature, particles will lose their energy and they just start coming together closer and closer and they
Yeah,
arrange themselves.
yeah,
That's what happens when you uh, solidify or when you freeze an ice water into ice cube, right? But we don't get a very perfect crystal, right? Why? Because the arrangement is not tightly packed.
yeah,
When they come together, not only water, any particle for that sake, when they come together, no, it is just randomly coming together.
yeah.
But when there is a force of attraction driving it, assisting it, a plus is looking for a minus, then that just comes, locks it. Then the minus locks a plus. So it gives a very perfect arrangement, leading to a very beautiful crystal formation.
But then what about the isotopes of carbon like graphite and diamond that form like these big giant covalent lattice structures?
Mm. Okay, so their diamond, it's different. Diamond isn't even diamond, no, though being a non-metal, it is exception in many different cases in their strength because non-metals are usually very brittle. They break
Yeah,
easily. But diamond
yeah.
is very hard and also very crystalline in nature. Because again, because of the bond, there is a very proper arrangement, right?
But it doesn't have an electrostatic attraction, does it? Like, there's
No,
no positives and negatives. It's
no,
just
very good,
carbon.
very good question. See, again, this is why the conditions are very essential. Both graphite and carbon, I mean, diamond are made of same element. Both are made of, and it is allotropes, isotopes, allotropes.
What's an allotrope?
Allotropes are different form of elements.
Ah, is it like carbon 12? No, that's an
Uh-huh.
isotope.
Yes, that's an
Carbon
isotope.
50, is that still an isotope? Never mind.
Yeah. So carbon 6, 12, carbon 6, 13, carbon 6, 14, all these are isotopes.
Isotopes. Yeah,
Having same number of protons, different number of neutrons.
yeah.
Allotropism is when same element is present in different physical forms in nature. They are pure.
Okay,
Diamond
yeah.
is also pure carbon. Graphite is also pure carbon, but in different physical forms they exist.
Okay,
And those are
okay.
allotropes. Okay. Even we have allotropes for phosphorus. Phosphorus, we have it as white and also
Yeah,
red phosphorus. Two colored phosphorus, same pure phosphorus, but one will be in red color, one will be in white color. So allotropism. Okay. And why the same carbon in the form of diamond is very crystalline in the sense it's again how they are formed, the condition, the temperature and the pressure and the time it takes,
Yeah,
right? Which makes them, which makes the carbon bond, right, in a tetrahedral
yeah,
structure, right,
yeah.
making it a crystalline. So what is different in these two? Basically, it is the condition in which they grow.
Okay.
So diamonds are made or formed in a very, very extreme temperature and pressure. Unlike what? Graphite,
Yeah.
right? So that is where it differs. And that is how diamond is also crystalline, right? So basically, it also has a very proper structure, very, not a very random arrangement. It has a very proper tetrahedral giant structure. It goes on.
So
Hmm.
even though it doesn't have electrostatic attraction,
Hmm.
it has this not random organized structure because of its conditions that it's
Yeah.
made in.
Yes, exactly.
Okay.
See the which is why it is an exception. We don't have we also have um silicon dioxide also. You would have seen. Have
Yeah.
you ever seen the sand particles under microscope?
No, not under. No.
Okay, you want to take a look?
Oh, yes.
So if you go to beach and if you pick the grains of sand, do you think it is crystalline or amorphous? What do you think?
Oh, they look pretty dewy and like not lustrous. I'm gonna say not crystal.
Not crystalline. Hmm.
Yeah.
Okay, I want to show you a picture.
Oh God, are they actually like very crystally?
They are actually. Okay, can you see?
Whoa, whoa,
So this is no every single grain of sand. You
whoa.
have plenty of shapes and
Yeah.
yeah, it'll be very beautiful. Just Google, when you're free, just Google sand under microscope. You'll come across a lot of beautiful pictures like this. So
But
basically you
why
can
do they not? But why do they not look lustrous when they're like all put together?
all put together. You know how glasses are made?
Isn't it by heating sand to an extreme degree
Melting
until
sand, basically. You
yeah,
melt the
melting.
sand, you
Yeah,
pour it back, it becomes
yeah,
glass. So
yeah,
the point is, this is made of silicon dioxide, and silicon dioxide has a very similar structure to that of diamond, just ditto, same tetrahedral structure, which is why these two, though made of completely non-metal, still has a very beautiful crystalline structure. But apart from that, other non-metals are usually amorphous. They are not very shiny, they are dull, they are brittle,
yeah,
right?
yeah.
The point is, ionic compounds are crystalline in nature, generally speaking. And
Uh-huh.
covalent compounds, the ones that are solids, are amorphous in nature, which means they are not very shiny. Not
Crystal
shiny in
or
the sense, yeah, they are not very
dull.
shiny, does not have any sharp edges, right? Um, yeah, and it is very coarse. Very, if you take crystals, they'll be very the surface will be very smooth, right?
Yeah,
Shiny. But amorphous would be very coarse, rough, right? So
yeah,
again, exception there would be diamond.
Mm,
Yeah.
okay.
All right. So let me get back to the board. So do you understand? So millions of such ions attract each other, tightly pack themselves, leading to formation of ionic compounds. And ionic compounds, because of this actual force of attraction, has very high melting
Melting points
and
and boiling.
boiling.
Yeah.
Though it looks very simple, and ionic compounds are very soluble in nature in water. You just put it in water, it'll dissolve, right? But we
Yeah.
shouldn't underestimate the ionic compound's strength based on its solubility. The normal NaCl that we use in our kitchen,
Yeah.
which readily dissolves, will need 802 degrees Celsius to melt.
Whoa.
Yeah. So this explains the attraction, right? The electrostatic force of attraction, the strength of it. And what happens when we actually melt? These ions will just come out of their lattice position. They are just taken out of its position. You just
Okay.
create more space between them,
Yeah.
right? Yeah. So ionic compounds, crystalline, we said, very soluble, we said, then high melting boiling point. Then talking about the electric conductivity, as a solid, it does not conduct electricity, right? For example, you just take two wires, put it inside your salt container.
Oh,
No, right? No
but
reaction.
it does when it's aqueous.
Yes, very good.
Yeah.
Why?
Or melted.
Wonderful. Because as a aqueous solution or as molten solution, it has ions, free moving ions,
Yeah.
right? Which conducts, carries the electricity, right? So these are the important things you have to remember about ionic compounds and ionic bonding. Coming to
Yeah.
covalent bonding, instead of, again, I hope you have learned, but still, I'll show you a simulation. Okay, so when I take two hydrogen, they share, right? So the maximum, since they have only one shell, the maximum they can go for is two
Two.
electrons.
Yeah.
And the electron that is shared is common for both species. So now both has two.
Yeah.
Now, if I take carbon, carbon needs four more electrons to attain octet.
Yeah.
So each electron is shared with
One hydrogen.
one hydrogen, which gives us methane molecule,
Or methane. Yeah.
correct?
Alkane.
Alkane.
Yeah.
Yeah. So if I add one more carbon,
Double. What
yeah.
was it?
So this is single bond. And yeah,
Yeah.
every time I uh, uh, share an electron, for example, here I represent
Yeah.
it with a single line, single bond,
Yeah.
right? So it is between another carbon. So
Yeah.
like this. So
Yeah.
carbon CO O CH3 CO H. This is an acid. CH3
This is
COOH, right? Ethanoic acid, acetic acid,
ah.
basically vinegar.
Ah.
Okay.
Okay. Yeah.
So you can see now if I have to write the structure, two pairs, which means two lines. double.
Uh-huh.
So everything else single bond.
Single. Yeah.
You understand? But covalent compounds, they do not have very strong force of uh, attraction. So now see, there is one other difference. When we talk about attraction in ionic, it is between plus and minus. Obviously, there is nothing
Mm.
else. But melting point and boiling point in covalent compounds is based on not the bonds like ionic. It is based on the force of attraction between two molecules themselves. For example, this is one hydrogen and one more hydrogen. So what is the force of attraction between these two hydrogen molecules? That is what decides the boiling point and melting point. Right?
Intermolecular force,
Yes,
isn't it?
intermolecular force. Very good. Which is why the nature of the compound, the chemical composition of the compound doesn't change in phase change. So I
Okay.
take carbon dioxide.
Mm.
Okay, let me clear it. I have scribbled much. So let's take carbon, oxygen, oxygen, carbon dioxide, right?
Yeah.
Carbon dioxide. Now, uh, there are a lot of other forces, intermolecular forces like hydrogen bonding, Van der Waals force, London force, all these plays an important role. But now understand that when two carbon dioxide molecules are together, they have a force of attraction between them.
Yeah.
And when I cool the molecule, when I reduce the temperature, these molecules come closer, and that
Closer
is where
together.
I form dry ice, the solid
Yeah.
dry ice. When I take it out, no, I just put it outside, it just fumes, no, it becomes gaseous carbon dioxide, which means carbon dioxide molecules are as such, there as such. Earlier in solid form, they are very close.
Yeah.
In gaseous form, they are apart. Nothing happens to the molecule themselves. The intramolecular force, which is the bond, is intact, right? So
Yeah.
don't confuse it with the energy of the bond, because that happens usually when we melt.
Inter and intra.
Yes, when
Yeah.
we melt and when we boil, only it affects the force
Inter.
between the molecules, intermolecular
Yeah.
force. Nothing happens to the bond themselves.
Intra. Yeah.
But in ionic, of course, both are the same, right?
Mm.
So obviously, when we melt, we are just pulling out the ions,
Yeah.
right? So that is different from covalent. You understand?
Mm. Yeah.
And naturally, this is not a very, there is no very big force here, which means covalent compounds have very low melting boiling point, which is why you
Mm.
can see most of the covalent compounds are gaseous molecules already.
Yeah.
Carbon dioxide, hydrogen, helium, diatomic molecules like hydrogen, nitrogen, oxygen, sulfur dioxide, carbon dioxide, monoxide, everything is um,
A gas.
gas and very bigger molecules, right? Only becomes a liquid and then solids, right? Iodine is a solid, I2, right? I2, iodine, we have it as solid with a very greater atomic mass you have as liquid
Yeah.
and solid. But usually it is very gaseous in gaseous state, which tells us that melting boiling point is very low,
Very low. Yeah.
right? And of course, does not conduct electricity. What else? Even though it is solid, they are not like metallic or not like ionic compounds, not very crystalline, right? Very brittle, very uh, dull looking. solids. Like sulfur is a powder, yellowish powder, right? Like you also get it as blocks of sulfur, not very shiny, just yellowish blocks. Phosphorus you have, colorful solids you have, but not very shiny, very crystalline, very amorphous, very brittle, right? Did I miss anything? I don't think. So these are the difference between uh, ionic compounds and covalent compounds.
Yeah. Actually, if
Hmm.
not, I know non-metals don't usually conduct electricity, but of course there's exceptions, right? Then why does
Graphite.
graphite conduct electricity really well?
Okay, that's very simple. Graphite, see, it is based on the arrangement of the graphite. It is
Okay.
like a honeycomb structure.
Yeah. 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 Yeah.
So if you look into any carbon, so for example, I'm picking this carbon.
Yeah.
How many bonds are there for this carbon? One, two, three.
Yeah.
Just three. But
Yeah.
every carbon has four valence electrons,
Yeah.
right? So here only these three electrons are involved in bonding. One electron is free.
Free. Oh, so then graphite creates its own like little sea of electrons.
Yes, it has uh, no unbonded electron, free electron.
Oh,
Every
okay.
carbon, every carbon has one electron, which means you have plenty of electrons available, which makes
Ah,
graphite a good conductor.
okay.
Right? Again, an exception here.
It's always the carbons.
It's not fun
Yeah.
without carbon. Chemistry is no fun without carbon. Yeah. Okay,
Yeah,
so
okay.
I think I've covered the basics. Solubility, of course, I told you. I think that is all that fine. So go through all this covalent model. So I'll just okay Lewis dot structure. All that we'll also see in the next class when we discuss how to draw again kind of basics which you might have learned. Then comes the
Yeah.
important part. Yes, very important. This is the actual DP concept, determining the structure of compounds. Right?
Okay.
Using VSPR theory will be very easy, very interesting. Okay, which will start. Okay, so apart from that, just go through all this structure 2.1.2. You have polyatomic ions. Just
Yeah.
go through all that. So I hope you know what are polyatomic ions. So for example, Cl minus is a monoatomic ion, just made of one atom.
Mm.
Polyatomic ions are ions made of more than one atoms. OH
Okay.
minus,
Yeah.
NH4 plus.
Mm.
So these are called polyatomic ions. It is good to remember the charge SO4 2 minus.
Yeah.
Yeah, if you remember all these charge, it is fine. At least what is given in your guide,
Okay.
right? Only few
Yeah.
are given 5, 6. Remember that. Will be very useful.
Mm.
Okay.
Yeah.
Yeah. So go through
Okay.
this.